Hi, I'm Matt Jarvis. So I'm a professor of astrophysics at the University of Oxford, and I also have a visiting professorship at the University of the Western Cape. And my research covers multi-wavelength extragalactic astronomy to understand how galaxies form and evolve over the history of the universe, and also how we can use those galaxies to trace the underlying cosmology. Today, I'm going to focus on the radio continuum science that we do and what we get from extragalactic surveys operating at radio wavelengths. So before I start, I'd like to thank a few people who have contributed a lot of the imaging and pretty pictures of this talk. So Catherine Hale, who's in Edinburgh, Ian Hayward also in Oxford, and Imogen Whittam in Oxford, but also Leah Morabito, who's in Durham, Matt Prescott and Jacinta Delhaize are in Cape Town, and the wider team behind what's called the MIGHTEE survey, which I'll come back to later. So what are the science goals of radio continuum surveys? So over the past 50 years or 60 years since we've had surveys in the radio, they've been used for two main things. The first is to trace the star formation history of the universe. So the synchrotron emission that we see in supernova remnants from massive short-lived stars are actually a direct probe of the star formation rate in galaxies. Because those massive stars are short-lived, the number of supernova we see going off from those stars actually tells us how many stars there are and how quickly they are forming. And one of the key bits of information that we get from the radio is because the radio wavelengths are quite long, so the usual operating frequency of radio telescopes is 21 centimeters or 1.4 gigahertz. And that means that the waves go through a whole lot of different things in the universe, including what we call dust. In much the same way that you can receive radio waves in your house because the radio waves travel through bricks and wood or anything in their way. And it's to do with the long wavelength nature of the EM radiation in the radio. So that gives us a relatively unobscured view of the universe at radio wavelengths, which is not true if we use other wavelengths to trace the star formation. The usual ones being the ultraviolet emission, which gets easily blocked by dust in the universe, but also the far infrared wavelengths, which actually trace how that dust has been heated up and then it re-emits in the far infrared. But our far infrared technology is limited in size, and therefore we have a very blurred view of the high redshift or extragalactic universe from far infrared wavelengths. So radio wavelengths really cut out a niche, and I'll come back to that later. And on the right here, you can see what we currently think of is the evolution of the star formation rate density in the universe. So on the x-axis here, we have redshift or look back time at the top, and this is, so we're at redshift 0 or time 0 on the top axis, and if we look back over the last 10 billion years, so 10 gigayears, we can see the star formation rate density, so the amount of stars being formed per unit volume, has increased by around a factor of 100 from, this is on a log scale or on the y-axis here, so it's increased from around 10 to the minus 1.7 per unit volume here to around 10 to the minus 0.8 or so. So it's around a factor of 10 or 20. There's a lot of uncertainties attached to this, but that 10 billion years of cosmic time, so we know the star formation has just been dying off in galaxies for the last 10 billion years, on average. Beyond 10 billion years ago, as we approach the Big Bang, around 13.5 billion years in the past, we can see that the points on here are a bit more sparse, so there is less data. And we see the star formation history is declining as we go to earlier and earlier times. So there seems to be a peak in star formation activity of what's generally now termed as cosmic noon around 10 billion years ago. I'll come back later in the talk of how we measure this. But that's sort of the science we're trying to get at, what's happening in terms of the build-up of galaxies over cosmic time. And this is all the galaxies. It doesn't tell us anything about which galaxies are forming all the stars and in what environments. So the other traditional aspect of radio continuum surveys is to understand how galaxies and their black holes are influenced by jet activity, and this is generally termed active galactic nuclei, or AGN activity. And this is due to accretion onto a central supermassive black hole in the centre of galaxies. Those black holes are roughly about 10 to the 8 or 10 to the 9 solar masses, so around a billion solar masses in size. And they accrete material from the centres of those galaxies. And in some cases, not all cases, but in some cases, they expel these massive and large jets that you can see on this diagram here. This fluffy emission in the red that you can see is actually the radio emission. And for a long time, these are the objects that were most well studied in radio continuum surveys because they're bright. They're the brightest things in the radio universe beyond our own galaxy. And therefore, we observe them in quite shallow surveys. So we don't have to have the most sensitive radio telescope to actually see these powerful beasts in the universe. And it's clear over the past 2 decades that this jet activity from AGN can have a massive influence on how galaxies form and evolve, particularly the most massive galaxies. And again, these jets, we detect them from their synchrotron emission. So the electrons accelerating in magnetic fields, and they emit this synchrotron radiation, which you should have heard about from Garrett Cotter's lectures. So they're the 2 main things we get from radio continuum surveys, but I think to understand galaxy evolution in general, we have to look at other things. So it's not just good enough to observe galaxies, we have to understand where they are in the universe. And this is sort of the influence of environment. Are they in galaxy clusters, which have massive bound structures of hundreds to thousands of galaxies, all gravitationally bound together in the same way as the solar system, planets in the solar system? And we know that the environment of a galaxy dictates or can influence how quickly it evolves and what it evolves into. So we also need to relate it to the environment. And this then naturally leads on to how do these baryons that we see in galaxies trace the underlying dark matter distribution, and therefore we start moving towards cosmology and the large-scale structure of the universe. And this is the dark matter simulation from the Millennium simulation, showing that this cosmic web where all the galaxy clusters form on the intersection of these filaments, where you see these bright blobs, and the galaxies tend to fall along these filamentary structures. And last but not least is actually linking this all together and with galaxy clusters themselves, and understand how all this fits together. Okay, so I think it's important to recognize that we can't do this just using radio emission. We have to use other wavelengths, and we use the whole of the electromagnetic spectrum to understand how galaxies form and evolve, all the way from the gamma rays through the X-rays, the UV, optical, infrared, and radio. And I've shown this plot. This is the actual what the integrated sky light looks like as a function of wavelength. So, and the higher this is on the y-axis, the more dominant it is in terms of the energy output in the universe. And you can see that most of the light in the universe is emitted at the optical and infrared wavelengths here, and the peak here in the microwave. Now, the microwave emission here is dominated by the cosmic microwave background, which is the emission that is permeated across the whole universe from the last scattering surface when the universe was very young. And galaxies do not contribute very much to that microwave emission. The galaxies contribute very much through the optical and the infrared, and all these here, although in the X-ray and the gamma rays, it's mainly the emission from accretion disks around black holes that are doing the bulk of the emission. But you can see the optical and the infrared represent the bulk of the emission that's coming from starlight or galaxies. And the radio plays a relatively minor role, but it is an important role, and it gives us different information to what we get from the optical and the infrared. So that multi-wavelength data is important for a number of reasons. So radio spectra, so if we actually look at what a continuum source looks like from the radio, it's just a power law. There are no features. It doesn't give us much information apart from how bright it is. And if you have 2 data points, it tells you that the steepness of the spectral index, or how steep the spectrum is in the radio. So what we need data at the wavelengths for is to calculate their redshift, so how far away they are, to enable us to start separating things like star-forming galaxies from the jetted AGN if we can't do it morphologically. If they're unresolved and everything looks like a blob, we don't know what's a star-forming galaxy and what's an AGN from the radio alone. And that extra information also gives us understanding of the mass of the galaxy or the star formation rate from a different probe like the UV or the far infrared. So it's important to have that other information. And just to highlight that redshift effect and how lacking it is in the radio. So this is the typical radio spectrum. So if the flux is on the y-axis and we have the frequency on the x-axis, you can see it's just a power law slope. And what happens if we redshift it just looks like a power law slope. So we have no information to actually obtain the redshift because we don't know whether it's got fainter because it's further away or just fainter, so less luminous. So we need that other information to determine things like redshift. So where we are now with radio continuum surveys is we tend to do them over areas of the sky which have excellent multi-wavelength data to enable more science to be done. And I'll come back to this when I talk about the MIGHTEE survey later, where we actually hit 4 of the most well-studied fields in the extragalactic sky, if you like, or so sort of 10 square degrees or 20 square degrees in patches of sky where we have a wealth of other information. An example of that is the video survey. You can see that when we look at the infrared wavelengths, we have around 1 million galaxies over a relatively small field of view, sort of around 3 or 4 square degrees. We have over 1 million galaxies in this image, which is way more galaxies than what we see in the very deepest radio data over this field, which is more like tens of thousands rather than millions. So that optical infrared data is very important, and it actually allows us to trace more things about the galaxy than just the radio. So just to summarize, this is what the spectral energy distribution of a galaxy looks like. So it has various components. So this is going from the UV all the way through to the far infrared. So that radio is off the end here and the X-ray is off the other end. But what you see, this is the starlight and the emission from the light that's generated from the stellar populations in galaxies. So at this end you have the UV, which traces the hot young massive stars, and thermal radiation from accretion disks around black holes. As we move to longer wavelength, but still in the blue, we start picking up the young and moderate age stellar populations through to the old populations as we go longward of 4,000 angstroms. And we also still pick up thermal radiation from accretion disks. Going slightly longer, in the near infrared, we tend to be dominated by very low mass but red evolved stars, which make up the bulk of the stellar mass in galaxies. And moving along, we see the dust emission. These peaks that we see in the middle here are something called PAH features, which are due to emission from complex molecules in and around the ISM of galaxies, the interstellar medium. But we also see this continuum emission as we go up into the far infrared, which is due to sort of dust, which I've mentioned a few times, but it can be thought of as sort of like smoke from a cigar. And as you know, when that gets hot, it glows a little bit. It glows blue in terms of what we see, but the dust we see in space actually glows at longer wavelengths in the far infrared, and we pick that up as thermal emission in the far infrared. And there's where the radio comes in as synchrotron emission, and it should be noted that even in the far infrared, it's not necessarily all thermal emission from dust. We actually see in some objects that the synchrotron emission from supernovae and jets can actually contribute to that far infrared emission. So the other thing that we have to do then when we have a radio survey is to get the redshift, we have to be able to cross-match it to that optical infrared data to be able to measure a redshift. So that's really hard to do a lot of the time, because when we have these complex galaxies which have jets and lobes and not just a single blob on the sky like we see in the optical, it becomes difficult to say which galaxy that we're seeing from the stellar light is associated with the radio emission. And so we sort of have to do that by eye. We go through tens of thousands of objects in the radio and cross-match them by eye, where the contours on here are the radio emission. In the top right here, you can see this typical double-lobed object where you see a lobe over here and a lobe over there. And in the center is a galaxy. You can see on the grayscale is a galaxy. And we pick out that galaxy as the host galaxy, and therefore we can then assign a redshift or a distance to it. And once we've got that redshift, we know how luminous it is. So its physical properties rather than just its observed properties. So all this fits together. So once we've done all that, we can go back to things like looking at this cosmic star formation history of the universe. And this is going back to that plot I showed earlier of the evolution of the star formation rate density, star formation rate per unit volume in the universe as a function of redshift. And I've added another plot here on the left-hand side, which shows you the contribution to this plot that comes from the unobscured and the obscured star formation. So the UV emission here is all this star formation that's traced in the UV wavelengths, which are those young hot stars, but we only see that UV radiation if there's no dust in the way. So this is telling us about the unobscured star formation. Whereas if we go to that far infrared wavelengths, we can pick up that reprocessed dust emission, the dust that's been heated by these UV photons and is then re-radiating in the far infrared. And you can see that the obscured star formation is a lot higher than the UV. It's actually, most of the star formation in the universe is obscured. But you can also see that our ability to measure the obscured star formation starts to wilt away at the very highest redshifts. And that's because of the technology we have for our detectors operating at far infrared wavelengths. ALMA, an interferometer in Chile, is trying to resolve this. It's actually a new powerful radio telescope, but operating at higher frequency than what I'm speaking about here. And it can start filling in this part of the spectrum. But it has to do it. It has quite a small field of view, so it's very difficult to do surveys with ALMA. So how do we even go about measuring this, the star formation history of the universe? So the first thing you do, and this is one of the most straightforward things you do once you've got a radio survey, you measure something called the radioluminosity function, which is just the number of objects per unit volume as a function of their radioluminosity. And on the left hand, on the plot here, there's a diagram from a paper by a postdoc in South Africa, Elliot Malafalo, who has done this with new data over one of these deep fields. And you can see what's plotted here. This is at low redshift, and as we move down here, we go to slightly higher and higher redshift, and it starts again, and it goes all the way out to redshift 4 at the end here. And what you can see is this characteristic shape. If you see something that is has a shallow slope at low luminosities and it gradually steepens, and then you have another bit that adds stuff at the end here at the bright radioluminosities. And that's because this is a combination of star-forming galaxies and active galactic nuclei. So what we see, the star-forming galaxies have this shape where they have a flat, relatively shallow slope and then fall off to high luminosities by these dotted lines here. And then this additional contribution is the bright things, the bright AGN, that are contributing to this radioluminosity function. And we've made no attempt to split up the points here, and it's just showing you how this affects the shape of this. Now, if we want to measure the history of star formation, what we need to do is know which ones of these galaxies, which galaxies that make up these luminosity functions are star forming. And that's quite difficult to do. So what Eliab actually did here was just take this model, parametric form for the radioluminosity function, this thing here, as the best fit given the data and what we know about the AGN here. So we adopt this fall off, and what you do to measure the cosmic star formation rate then is just integrate under this curve. And if you integrate under this curve, you get a data point at redshift 1/2, a data point at redshift 0.7 here, and a data point at redshift 0.9 here, and so on. So you can start building up that evolution of the cosmic star formation rate density. And if you do that, you get a plot like this, which looks very similar to the plot I showed earlier of this from McDowell and Dickinson, this evolution of the cosmic star formation rate and this turnover around redshift 2. So this is it derived completely from the radio now, this blue curve here, and the grey curve is something is a study using far infrared wavelengths, and you can see there's a difference here, and there are a whole plethora of reasons why that could be. It could be that either this is wrong, which could be the case for, or it could be that we're missing some of the galaxies that contribute to this, which is also a valid possibility. But what you can see is you build up this history of cosmic star formation, and out to redshift 1.5, we agree across all wavelengths, and then we fall short of the measurement from the far infrared, but we actually stay higher than what you expect from the optical. So we're still picking up things that you don't see at the optical wavelengths. So that's how you do this. So that's just an example of what we gain from radio continuum surveys in terms of the star formations. So what about AGN now, these accreting black holes? Well, this is another luminosity function, but this is a luminosity function plotted in near infrared in the K band at 2.2 microns. And confusingly, the brightness is going the wrong way. These are absolute magnitude, so brighter objects are to the left here. But the axis on the y-axis, the y-axis is just the number density per unit magnitude in this case. And this is a plot from quite a while ago now, around 2003. And the blue points here are the data from various surveys, and the lines are simulations of galaxy evolution. And 20 years ago, what we were finding is all the simulations were predicting this dashed line, which really didn't agree with the data. And the reason for that, why we think that happens, is that those models around 20 years ago weren't incorporating the effects of this black hole activity in the center of galaxies, and what's now generally termed AGN-driven feedback. And what the AGN do, in particular these jets, can actually stop stars forming. So when you stop stars forming, they don't get as bright as they would have done, essentially. Those galaxies don't get as bright as they would have done because there are fewer stars in them. And what that means is that dashed line gets pulled back to that straight solid line there, and it tends to fit the data better. Now, there's lots of very difficult physics in here that I'm glossing over, but that's the general idea, that if you set one of these black holes, if you ignite one of these black holes and it generates this massive plumes of radio emission, that radio emission can stop gas getting onto the galaxy and start forming stars. And therefore your galaxies don't get as big as they would have done without that. So here's a more pretty picture of one of those radio galaxies. And you can see the bright galaxy, well, the center of the nucleus of the galaxy in the middle here, the bright emission from around the central supermassive black holes, and these massive jets that are huge jets that are far expanding beyond the realms of the galaxy itself. The galaxy here is very small in comparison to the size of these jets and the size of these what we call lobes. And all this emission here is the synchrotron emission from electrons spiraling in magnetic fields. And just so you see that, here's the optical picture which shows you that galaxy. You can see the core of the galaxy here and the general fuzz from the stars all the way out here. But you can see that this the radio jets extend far beyond this. So these are amazing objects, and they contain a lot of power and a lot of energy. So how do we think we get these? So there's many theories behind how these jets are generated. The most well studied, I guess, is that you have a black hole with an accretion disk. The gas falls onto that accretion disk and towards the black hole, and with magnetic fields in and around the black hole, that emission starts spiraling out, ejected along those magnetic field lines, and you see a jet. And some studies will say you need a spinning black hole to generate these, some others don't. Fundamentally, this is a really difficult problem, and we don't have much information going from the very central regions of these supermassive black holes because we don't have the telescopes to study it in that fine resolution. But that's the general idea. And here's another pretty picture of these. They come in all shapes and sizes, but I think it's fair to say that they come in all shapes and sizes, but their mechanism for how they disrupt the gas flows and the star formation in galaxies is pretty poorly understood. So there's a lot of work to be done on this, both on the theoretical side and on the observational side. Back in the 1970s, these types of radio galaxy were classified into two types, something called Phaneroff-Rayleigh Class 1 and Phaneroff-Rayleigh Class 2. And you can see that the general idea is here that the FR1s, Phaneroff-Rayleigh Class 1s here, are bright at the centre and they get fluffy at the edges. So you have the jets close in, then they sort of just peter out at the edges. Whereas the FR2s have these very strong jets coming out here, but they have way more emission out at the lobes and what we call the hotspots of the lobes. And these tend to be the higher power sources, and the FR1s tend to be the lower power sources. More recently, there's been a growth in understanding these radio galaxies, and as we go deeper with new facilities, if we get more sensitive information, then we start seeing different populations. And we actually find that nowadays, if you look at in deep radio surveys, a lot of these AGN-powered galaxies are actually very compact. We don't see these massive jets and massive lobes. We actually see a lot of compact things, which are actually relatively small. And there are any number of reasons why this could be the case. For a long time, people thought these small radio galaxies were due to the fact that they just started, so they hadn't had time to get out to these the scales of the bigger sources. But I think the general consensus is now it's probably a mix of things going on. Some are just intrinsically small. They don't have the power or the energy to get out to those bigger radii, and some of them are probably young and just are have only just started their activity, and again haven't had the time to get to that extent. And again, these are all lines of current research to understand what's going on here and what the different types are doing. One thing that has come around in the last 5 or 6 years, I'd say, is moving away from this morphological classification of what's an FR1 and FR2 and try and relate more to what's physically going on in terms of the accretion onto galaxies. And this term is generally called a high excitation radio galaxies. And unsurprisingly, the other category is low excitation, but I'll come on to that in a moment. So the high excitation radio galaxies are thought to be powered by accretion of cold gas from a geometrically thin, optically thick accretion disk, which is very efficient at of moving stuff towards the black hole, and therefore you get a lot of energy out. That's opposed to a slightly thicker disk, something called an advection-dominated inner accretion flow here, which is inefficient in its accretion. It's inefficient in how it can radiate, and therefore we don't see as much energy coming out of it. And these are generally separated by virtue of what they look like at optical wavelengths or near-infrared wavelengths, because the efficient accretion, the high excitation, generate a lot of power across the whole of the electromagnetic spectrum, whereas the low excitation radio galaxies don't look very special at all at optical and infrared wavelengths, but we still see a lot of radio emission from them. So their differences lie in the optical emission rather than in the radio. We actually see a mix of radio emission in both populations, but their accretion is completely different. So these, when you hear people talk about HERGs and LERGs, this is what they're referring to. And there's been a wealth of studies on these over the past few years. And going back to how we combine this with the optical infrared data, we can start understanding what kind of galaxies these different AGN reside in. And the general consensus in the relatively low redshift universe, so out to redshift 0.2, 0.3, is that those high excitation radio galaxies tend to reside in slightly lower mass galaxies than their low excitation counterparts. And they tend to have slightly lower black hole masses. And the lower left plot showing here is those low excitation objects have a higher, what we call the DN4000 here, which basically means they're in older galaxies. So the higher the value here, the older the galaxy is, or the older the stars in the galaxy is. Whereas a high excitation galaxies tend to lie in galaxies which are slightly younger. And this is just telling you about how compact those galaxies are. So that at the very low luminosities here, it seems that the high excitation objects that live in galaxies are slightly less compact than, slightly more compact than, get this the right way around here, more compact than the low excitation, but there's little to choose in terms of the general size of these. But the other trends are pretty solid. So once you have these jets going off, what they do is they can influence how gas flows onto the galaxies from those filaments that I showed you from the simulation earlier. The gas tends to flow along those filaments, but if you've got powerful jets going off, it can stop that gas falling on, or it can expel gas completely from the galaxy, and that gas can then not go on to form stars. And both the HERGs and the LERGs can do this, but the thing with the LERGs is they actually, because of the way the jets work compared to how much gas there is, they can have a greater effect at low redshift, where in the massive galaxies where there's a lot of the galaxies reside in galaxy clusters. Whereas at higher redshift, the radiative or the HERG can actually have a bigger effect, because there are way more black holes operating in the HERG mode at higher redshift compared to the LERG mode, and vice versa. So both these things contribute. Again, the physics behind this and how it actually works is pretty poorly understood, and various hydrodynamic simulations try to address this in various ways. I suggest none of them get it completely right, and it's pretty much a bit of a fudge at the moment, so that, again, there's a lot of work to be done. Okay, so what are the unanswered questions we have in galaxy evolution and in terms of these AGNs? So how does the radioactivity relate to the host galaxy properties? You've seen some information on that, but only in the very restricted view in the local universe. Is there a real dichotomy between the high excitation and low excitation radio galaxies? Again, our statistics up until now have been pretty limited. How do they evolve? What happens when a jet turns off? Do we still see those electrons? I think we do. We have cases of those. Why do some radio galaxies not produce the most powerful jets? What is it going on around the accretion disk and the black hole that means we see some powerful jets and some others? And how does the environment influence this? Going back to that question of whether it's nature versus nurture. Does it matter what environment galaxies in order to what we see in terms of the AGN? And how does this depend on radio power, redshift, and all the other free parameters we could put in here? So they're the two areas of science that are most relevant for radio continuum surveys in terms of star formation and the AGN. So I'm just going to finish the talk with where we are now in terms of radio continuum surveys. And I'm going to focus on the MeerKAT telescope in South Africa, which is the most sensitive survey telescope in the world right now, operating at these frequencies, and it's an amazing instrument. It has 64 dishes, each of which is 13.5 meters, and they're spread across 8 kilometers in the northern Karoo in South Africa. And it operates between 850 megahertz to 3,500 megahertz. And it will eventually be built out into the square kilometer array. So why the Karoo? Well, it's no people and therefore no microwave ovens or mobile phones, which affect how we can do our radio observations. It's dry and has lots of space. So that means we can build a big telescope there as well. And then this is the sort of thing it can do. This is sort of a departure, but it's just a pretty picture. This is a view of the galactic center from MeerKAT, with the image processed by Ian Haywood. And this was presented at the inauguration of the MeerKAT telescope as one of the first observations done with MeerKAT. You can see all this amazing structure around the galactic center. The black hole in the center of the galaxy is in here, something called Sag A star. All this other stuff you can see, these tight filamentary structures, are due to, again, electrons in magnetic fields. Why those magnetic fields are so straight and defined, we don't know. All these bubbles and bits you can see around the edges here, they're supernovae remnants. So stars have exploded at the center of our galaxy, and you can see these shells of emission expanding outwards. So there's a massive amount of information there, and MeerKAT sees all this. And this is one of those radio galaxies I showed earlier, viewed with MeerKAT. You see this massive amount of information, all these different bits of structure within these massive lobes coming out of the center of the galaxy. So what is the MIGHTEE survey doing? So MIGHTEE is doing a survey of around 20 square degrees in 4 different fields on the sky with the aim of understanding the formation and evolution of galaxies. It actually has 3 components. It's not only a continuum survey, it's also a spectral line survey, which you'll hear more about from Anastasia later. But it's also a polarization survey as well. It's able to look at the polarization of the radio emission and therefore give us more information on the magnetic fields. So why is MIGHTEE MIGHTEE? It's a unique combination of depth and area. So it doesn't just go deep, it goes wide enough to make sure that we can see how galaxies are residing in this large scale density field that we know that the universe is distributed, all the matter in the universe is distributed around. So we should get a census of how galaxies form and evolve in different environments, which is that leading back to that environment question, nature or nurture. MIGHTEE observations are underway. We've had, this needs to be updated, we've run around 800 hours of time now, and we have science ready imaging, which I'm about to show you. So these are the pointings across the 4 fields. There's more in some because some fields are just smaller in terms of the amount of data they have, and some are bigger, like these 2 over here. And this is where we are. This is where we were last year anyway. So this is 2 of the fields. This is called the Cosmos field, and this is the XMM LSS field, the details of which you don't really need to know. But the key point is this is the size of the full moon here. So that gives you an idea of the area on the sky we're observing. And in here, there are around 10,000 independent radio sources, individual radio sources in that area. And there are around 25,000, 30,000 in this. So that was last year. We've now grown that to this, so it's expanded out. And these are the complete areas that we surveyed in these 2 fields now. You can see lots of small dots. The small dots tend to be the star-forming galaxies, whereas the big jetted things are those AGN I've shown you before. And it's not all straightforward when you're doing radio observations. This is just an example of if you do what we call second generation calibration of the radio data, this is what it looks like. So if you just did the most straightforward, a pretty straightforward but robust job on reducing and analysing the data, this is what you get. But if you introduce new techniques that have been developed over the past few years, you can get rid of that problem source down in the bottom right and get a much cleaner map and less noisy. So you go deeper by doing things. And again, every dot on here is an individual galaxy. And you can see at the side here some extremely pretty, powerful radio galaxies with various structures. Something looks like there's a double radio galaxy here with 2 nearby things. It may just be a chance alignment or actually interacting. So we need to understand these more. So how can MIGHTEE help us understand radio galaxies? Well, we have the depth to go all the way out to redshift 6, so way past the peak in that star formation rate density plot I show you, out to around 11, 12 billion years in the past. We're deep enough to go down to the quite low star formation rates, but have the area to pick out rare, powerful AGN as well. And we probe different environments, and we have that excellent multi-wavelength data that gives us the redshifts and look at the stellar populations as well. And you can do things like this with combining all those radio galaxies to understand what they are. So you can use various techniques. You can see if they have X-ray emission, which tells us about the accretion disk. Where they have mid-infrared emission, tells us about hot dust that's been heated by the accretion disk. And we can also see if they've got signs of an optical AGN, so do they look like what we call the quasar? And you can do all these things with the data we have, so we can start breaking down the radio sources into constituent populations of AGN or star-forming galaxies. And a nice, I thought I'd show a nice picture here of what we do pick up, and this wasn't found, and this is very much down to the very large surface brightness sensitivity that MeerKAT has. We found 2 giant radio galaxies in this relatively small field. And what do I mean by giant? Well, they're 12 arc minutes across on the sky, which is around 2 megaparsecs in size. So these are huge. And here's one here that I've zoomed in on the bottom right. And interesting, this is a good example of what MeerKAT picks up that you actually don't see with another interferometer, which is really sensitive as well, but has a different baseline distribution. And the way interferometers work, that other telescope doesn't have short baseline, so it's not as sensitive to diffuse emission. So even though the VLA in America has a similar sensitivity to MeerKAT, when we see that with the VLA, it's very hard to pick out that emission, but MeerKAT does it really well, and that's due to its surface brightness sensitivity. I'll just blink between those. You can see that MeerKAT does a fantastic job of picking these out. And more information on this is it was in a paper led by Jacinta Del Hayes in Cape Town, and based on what we knew about these giant radio galaxies before, the probability of finding these GRGs by chance in this relatively small field was around 1 in a million. So this tells us that these are probably way more common than what we thought, and it was the fact that our telescopes weren't sensitive enough to this kind of structure and these kind of objects that we've missed them before. And with MeerKAT, we should detect way more of these. And you see that the one on the left is 2.5 megaparsecs in size, and the one on the right is around 2 megaparsecs. So these are huge radio galaxies. So hopefully that gives you an overview of the kind of thing we do radio continuum surveys and the current state of the art. The key messages are radio continuum surveys of the extragalactic sky provide information about the formation and evolution of galaxies, which we can't get in other wavelengths. And in particular, they trace the star formation by measuring the synchrotron emission from supernova, which is not, which just permeates through the dust. It doesn't get stopped by the dust, so we have a relatively unobscured view of what's out there. And the other population we pick out are those jetted sources, the AGN, with accretion onto a central supermassive black hole, which then results in this massive amounts of synchrotron emission from jets and winds. However, the real take-home message is the key insights are gained from combining all the wavelengths together, and it's only then that we get a complete overview of all the key phases in the galaxy's life. And you do that by making sure you're observing the same galaxies at all those wavelengths, so you're carrying out the surveys over the same patches of sky, so you can bring all that information together. Okay, I'll stop there. I hope you enjoyed it or found it informative, and thank you.